Hi everyone. Today's tutorial will be regarding logic gates. So what is logic gate? Logic gate is a device that acts as a building block for digital circuit. They perform basic logical function that are but fundamental to digital circuits. Most electronic devices we use today will have some form of logic gates inside them. So, for example, logic gates can be used in technologies such as smartphones, tablets, as well as computers and memories. Now, there are seven basic logic gates, which I'm going to explain to you one by one. There is AND gate, there is OR gate, XOR gate, NOT gate. Now, the NOT gate is the 0, 1, or 1, 0, and that's it, which I'll explain that to you in a minute. NAND, it's basically the negative of AND gate, NOR negative of NOR gate of OR gate, and XNOR, which is a negative of XOR gate. Now let's have a look at the NOT gate. I start normally. We don't start with NOT gate. Normally we start with and then we go through OR, and then we cover the NOT. But I'd like to cover the NOT gate first, as it's easy to remember and it's easy to forget. So NOT gates act as an inverter, and sometimes called a NOT gate, to differentiate it from other types of inverter. So because it has only one input, it reverses the logic state. So if the input is 1, then it's the output 0, and if it is 0, the output is 1. And this is how it looks like with the circle at the top or front, as in to show the NOT gate. And as you can see, it's just one input, one output. Now we have AND gate with two inputs. So the AND gate is the name of the gate, and if it's 0, it's called false, and is 1 called true. So the gate act in the same way as logical and operator. So the following illustration and table show the circuit symbol and logic combination for the AND gate. So if you look in here, as you can see, when the input is 0 and the output is 0, sorry, the input 1 is 0, input 2 is 0, because I'm used to A and B. So if the A is 0, B is 0, then the output here will be 0. So when we have A, B, and let's say this is C, if it's 0, 0, then it gives me 0. Now, when you do logic gate, the first thing you do, if you have two inputs, you list your zeros and ones. So the first input will be 0, 0, 1, 1, and the second input 0, 1, 0, 1. That is fixed. You always have to do that, which I will show you with OR gate in a minute. So when it's 0, 0 is 0. When it's 0, 1, then it's 0. When it is 1, 0 is 0. If it's both on, then you have it on. Now let's look at the NAND gate. So as you can see, the NAND gate exactly like the in terms of the diagram as the AND gate. However, there's like a circle at its top, which is the inverter. That's why it's negative AND. Yeah. So here we have, so whatever output you get from the AND gate, you basically invert it. So if we have 3 zeros and 1 here, there's going to be 3 ones and 0. Yeah, and then again, as you can see, 0, 0, 1, 1, 0, 1, 0, 1. That's you have it by default. Because the reason why, because we only have, if it's two inputs, we only have 4 options or 4 choices. It's either both off or both on, or the first one on, off and the second one is on, or the second one is on and the first one is on and the second one is off. There's no more because it's just two inputs. So we don't have any more choices apart from this. Now OR gate gets the name from the fact it's behaved after is the fashion of the logical inclusive OR. So the output is true if either or both of the inputs are true. What does that mean? If any of the inputs is on, then the output will be on, unless they're both off, and that is basically goes off. And that's how it looks like in terms of the OR gate, the shape of OR gate. So when we both off, then it's off. Any of the input is on, then we have it on. So by now you should know what NOR gate will look like, which is a negative OR. So we'll have a circle here, an N is before the OR, and rather than 0, 3 ones, it's going to be 1, 3 zeros. Yeah. So the NOR gate is basically the inverter of the output from the OR gate. Now we have another gate which is called XOR. XOR, or exclusive OR. As you can see the shape that looks like, it looks like OR, but there's like some sort of like an arch here. So the output is, if the output is true of either but not both of the input are true, the output is false. So as you can see here, when we have input 1 and input 2 both 0, then we have 0. If any of them is on, then we have on. But if we have them both on, then the output is also off or 0. Now we have XNOR. So as you can imagine, it's exactly like this with a circle and inverter of that. And this is XNOR, or exclusive negative OR. Now, so let's have a look in the real life how it looks like, for example, XOR gate. So XOR gate here is a combination of the following gates: 2 NOT gates, 2 AND gates, and 1 OR gate. When we put them together, we get XOR. Yeah, so if you think about it, the 3 basic blocks of building as the logic gate or the circuit here, we have this AND, OR, and NOT gate. Yeah, so by adding 2 ANDs, 1 OR, and 2 NOT gates, we have XOR gate. So if let's look at this truth table of this previous example here. So as you can see here, we have the switch 1, we have switch 2, or input 1, input 2, or A or B, and then we have the light bulb, which was the output. So to help you visualize what is happening on the XOR gates, let's use this pseudocode. So if input 1 XOR input 2, then turn on the light. Yeah, if input 1 XOR input 2, then turn on the light. If input 1 and input 2 are different state, then the if statement evaluate to true and then block executes. However, the inputs are the same state, then the if statement evaluate to false. So what I'm basically saying here, if we go back to XOR gate, if both off, it's off. If any of them on, is on. If both on, also off. And I leave it to you to apply XNOR to exercise also with NAND and NOR gates. Because all you got to do is to see this is the NOT gate, this is the AND, this is not NAND, it's AND, and here OR gate. If I want basically NOR, then we put NOR gate, which is, here we go, NOR gate, a circle at the front. So let's have a look here at the summary of basic logic gates, as well as understanding the shapes, the diagrams of the actual gates. We also need to understand in terms of the expression. Okay, so for example, A, as you can see here, is the input. Not A, we just put like a line on top of it to represent not, or sometimes we put a comma at the top. Yeah, that's also to represent the not. Now the A and B, sometimes we put A and B, sometimes we put A and infinity B, and then sometimes we put A dot B also to represent A and B. And also sometimes we put A with B together without anything in the middle as in multiply, and then that also counts as A and B gate. Now in terms of the OR, sometimes we use this symbol to represent OR. Sometimes we also use the plus symbol to represent OR gate. So A OR gate, or sometimes we can just put OR. Now, With XOR gate, now it's the plus of the OR, and then we circle around it. So that represents XOR gate. Now, NAND gate is just AND gate with a line on top of it to represent the negative, just like here. With the OR, it's going to be common sense, the same thing. And then we just put that on top of it to represent the OR gate. Now, in terms of the XNOR, so that you have the XOR gate with a negative, with a line right on top of here, and that will make it basically XNOR gate.